Hello class! In this video, I'm going to walk through some examples for how to calculate mass ratios and how to get formulas and particle diagrams for compounds that have those mass ratios. First, let me start off by explaining why this is important. In the 18th century, scientists were trying to figure out formulas for all of these compounds that they were creating and had new properties for. When they were developing all these elements and all the compounds, it's nice to know what the compounds are made of. Avogadro came along and had his hypothesis, which we've seen in class and worked really well for substances that could be gases. So anything that you could gasify worked really well with Avogadro's hypothesis. Not everything on the periodic table can become a gas, which is why we have to look at mass ratios. This is what helps us figure out your formulas and your compounds for things that are solid. So let's start off by looking at compounds that are formed with mercury and oxygen. First, these are two different elements. They form multiple compounds. That's our law of multiple proportions, is that our elements can combine together to form different compounds. Each of those compounds have a fixed ratio, so how many mercuries to how many oxygen atoms. In compound A, we've measured out scientifically, mathematically, and experimentally that compound A contains 85.11 grams of mercury and 6.79 grams of oxygen. A completely separate compound has 50.7 grams of mercury and 2.02 grams oxygen. In our first question, we're asked to determine the ratio of mass of mercury to mass of oxygen in each of these compounds. Well, ratios is just division, so anytime you see this type of fraction, we're going to do exactly what it says. We're going to take our mass of mercury, divide it by the mass of oxygen, and we're going to do that for each of these compounds. So for compound A, we had 85.11 grams of mercury, and we're going to divide that by the grams, 6.79 grams of oxygen in compound A. And if we have our calculator and we divide those, 85.11 divided by 6.79, we get a ratio of 12.53. If I was to do the same thing for compound B, taking my mass of mercury divided by my mass of oxygen, I'd have 50.7 grams of mercury divided by my 2.02 grams of oxygen. And that would give us 25.099. I'm going to round that so I have two decimal places, similar to how I had two decimal places here. So that would round to 10. These are my mass ratios, and I took these two fractions, turned it into one number. If I wanted to keep this as a fraction, it would be the same amount here. So in order to turn this one number into a fraction, I would put it over 1. So 12.53 divided by 1 would keep this as a fraction, just how this is a fraction. Because mercury was on top, my 12.53 would refer to mercury. My oxygen on the bottom, this 1, refers to my oxygen. I can do that same thing for this other compound. Again, to put it into a fraction, I just need to put it over 1. Now, for part B, how does the mass ratio for compound B compare to that in compound A? Sometimes the numbers are easy enough that you can look at it and know. Let's assume that we can't do that. In this case, you might be able to, but let me walk you through how you could figure this out if you don't have really nice numbers and can't visually tell. In order to figure out how one compares to the other, we need to figure out how many times bigger this one is to this one. So if I took the bigger ratio divided by the smallest ratio, it would tell me how many times bigger my big one is. So if I do my 25.10, because that's my bigger ratio, I'm going to divide it by my smaller number, which was 12.53. 25.10 divided by 12.53, I get 2.003. Round that to a whole number, this is 2 times bigger. So the ratio for compound B is 2 times larger, or 2 times bigger, or double the ratio in compound A. C. Sketch particle diagrams for the compounds A and B that account for these mass ratios. Okay, one assumption that we're making for all of these compounds is that your simplest ratio, your smallest ratio, is going to be one element to one element. That is the assumption that we're making. That is a huge leap that we're taking. But we've seen evidence for that in our previous worksheets. Anytime it's a simplest ratio, it's going to be a 1-to-1 ratio. So up here, my smallest one, which was my 12.53, that was compound A. Because it is the smallest ratio, I am going to assume that compound A is a 1 mercury to 1 oxygen ratio. So compound A is 1 mercury to 1 oxygen. I'm going to come down here and actually write that formula. 1 mercury to 1 oxygen. Again, that is because it is the smallest number here. Now, if I was to draw a particle diagram for this, this is saying that mercury is 12.53 for every 1 oxygen. And in order for these to be a 1-to-1 ratio, we learned in class that mercury has to be heavier, whatever the ratio is. So in this case, mercury is 12.53 times heavier than oxygen, which means that my mercury particle is going to be considerably larger than my oxygen particle. Now, something to keep in mind, when I was making this worksheet, I had to build this from scratch, so these were numbers that seemed to work and match the formulas. It seems a little extreme that our 12.53 mercury is 12.53 times larger than oxygen. This might not be scientifically accurate, but it was how the numbers worked out in order to have more practice problems. So bear with me if they're not the perfect numbers. And that's going to be our compound A. Now, compound B. We need a formula, a particle diagram as well as a formula for compound B. We know that B is 2 times bigger than our compound A. So I have 2 times more of something in compound B. That 2 times more is going to refer to my mercury. And I know it's my mercury because this is 2 times bigger on the top. My numerator is 2 times bigger. If I was to multiply anything by 2, let me come off to a side thing. Anything times 2 is technically 2 over 1. So I want the 2 to refer to my numerator, which is my mercury, and my oxygen would be referring to my denominator. If I had said half, then my 2 would be referring to the denominator because half would be 1 over 2. I didn't say that though. I said 2 times bigger. So I'm looking at 2 times of whatever my numerator is, my substance on the top. Another way that we know it's mercury is because I've got twice as much mercury here as here. We said that the 25 was twice as big as my 12. Well, down here I said that was a 1-to-1 ratio. In order to account for there being more mercury, our mercury didn't change its size from one compound to the other. It has to stay the same size. In order to account for there being more of them, we have double our amount of mercury. So my mercury would look something like this, where this is mercury, and this is my oxygen. That is how I get 2 times bigger, because it's the substance in the top on the numerator. It's also the larger number, and I know it's 2 times. So I have twice as much mercury. My formula for this substance would be Hg. I've got 2 of them, and then O, Hg2O. Let's try another example. Compounds nitrogen and oxygen. Again, these are the 2 elements that are combining. They form compound A and compound B. So same idea, our value of the ratio oxygen to nitrogen. We've got to take these masses and divide them. So 30.6 grams of oxygen divided by the corresponding number of nitrogen, 26.8 grams nitrogen. When I plug that into my calculator, double check that it works in your calculator, but to save time, I got 1.14, and that would be oxygens to 1 nitrogen. Same thing with this other compound. I'm going to take my 104.4 grams of oxygen, divide that by my 45.7 grams of nitrogen. If you plug that into your calculator, you should get 2.28. And that refers to my oxygen for every 1 nitrogen. How does the mass ratio for compound B compare to that of compound A? This one's a little easier to see visually. 1.14, if we double that, it'd be 2.28. But again, if you couldn't see that visually, one way to figure out how big it is would be to take the 2.28, which is my bigger substance, my bigger ratio, divide it by my 1.14, and if we plug that in the calculator, we get 2. So it says that this is 2, let me write it as a whole sentence. Compound B is twice as large, or 2 times bigger, or double the ratio of A. All right, now let's draw particle diagrams for this. So again, I am assuming that our smallest ratio is going to be a 1-to-1. In this case, my smaller one is compound A. So because this number is smaller, automatically A is my 1-to-1 ratio. So 1 oxygen to 1 nitrogen. And I've got 1.14 to 1. If I look at this being our sizes, my oxygen is larger than my nitrogen. It's 1.14 times larger. Roughly about the same size, but my oxygen would be slightly larger. So if this is oxygen, this is nitrogen, it might look something like that. Again, we have a 1-to-1 ratio. We could write it ON or NO. Right now we haven't talked about which order of letters they go in. We'll cross that bridge eventually. Compound A, 1-to-1 ratio because it was the smallest number here. Now, compound B. We said it was twice as large as A. Well, what is twice as large? Again, if I look at my numerator, because that's the number that's changing, my denominator stayed the same. My numerator is the top number, which refers to my oxygen. So I have twice as much oxygen. That's what's causing my mass to be higher. I have twice as much oxygen than in compound A. Well, here I had 1, so twice as much oxygen, I'd have 2 oxygens. I would still keep my 1 nitrogen. So this might be a particle diagram for my substance B, where this is oxygen, this is oxygen, this is nitrogen. My formula then would be NO2. You could have also written that as O2N. Again, it doesn't matter. We haven't talked about it yet. Try number 3 and 4. Go ahead and pause the video. Try number 3 and 4 with the same process. This is what I got for number 3. 0.351 and 0.176. That means that A was double of B. Again, this might not be visual, so I took the bigger divided by the smaller, came up with a ratio of 2. So that means A is twice the size of B, so A is double. If we were to sketch our particle diagrams for this, my simplest, smallest ratio is compound B. So that would become my 1-to-1 ratio. Because it's the smallest, I'm assuming it's a 1-to-1 ratio, which would be HgCl or ClHg would be fine for what we know right now. A is double that of B. Well, what's the doubled process? It's whatever's on the top, our chlorine. So A would have twice as much chlorine, double the amount of chlorine to get our ratio. So our formula, would be HgCl2. We're doubling what's ever on top. If you looked at substance 4, or question 4, we had 0.180 and 0.540 for chlorine to gold. If we figured out how much bigger that would be, bigger divided by smaller, we get a factor of 3. So B is 3 times larger than my ratio for A. Automatically, because this is the simplest one, that puts A as a 1-to-1 ratio. So we'd have 1 gold to 1 chlorine. In this case, 0.18 chlorine is our size to 1 gold, so your gold is actually bigger than your chlorine atom, because this is a bigger number than your 0.18. So that's why I drew AU as a larger circle. It's a 1-to-1 ratio for compound A because this is my simplest one, my smallest ratio. We said that compound B was 3 times larger. Well, 3 times larger in what? Whatever we had on top. So we're going to have 3 times more chlorine than we did in substance A. A had 1 chlorine, 3 times more. I'm going to have 3 chlorines in my compound B. Formulas for that would be AuCl if it's a 1-to-1 ratio, and AuCl3 if it's my 1-to-3 ratio. Hope that was helpful. Come see me in class if you need some one-on-one help.